The next topic I want to cover is bulk loading B plus trees, which is very important in practice. Now suppose that you're given a table, it's already populated with lots of records, and we want to build a B plus tree on top of it. Well, you might say, okay, why don't I just insert the records of that table using my insertion algorithm one by one? This would be terribly inefficient. Let me convince you why. Assume that you get this file in some random order on the field that we want to index. So let's assume we're indexing single letters, and we get the letters in this crazy order, CLZ, and so on. And we're going to build an order 2 B tree. Now, if you saw the interactive web demo that I talked about before, you can try this in the demo, and you'll see what's going to happen. But I'll talk about it in the next couple of slides as well. So as we start loading this data into a B plus tree, what we're going to see is that for every item we insert, we're going to search from the root to the leaf, looking for the right leaf to insert it on. That's already kind of annoying in the sense that we already know we're only doing these inserts. The second thing you'll notice if you do this experiment with the interactive tool online is that the leaves and the internal nodes most of the time will be half empty. This won't be a very full tree. Okay, and so we're not going to get very good space utilization out of doing multiple inserts. We'll have a tree that's mostly half empty. Finally, and probably most importantly, because we're inserting this data in random order, we're going to be modifying random pages in the B tree all the time. Every item that we insert is going to wander down to a different leaf and then cause updates to a different leaf. And what this means is we're going to get very poor cache efficiency. We're constantly going to be paging pages off the database into and out of the buffer pool. We do a lot of IOs. So there's a technique called bulk loading that's going to be much smarter. And here's how it's going to work. First, we're going to sort the input records by their keys, and we'll learn a good algorithm for sorting shortly. Then, given the data sorted, we're going to start filling the leaf pages. We're just going to create leaf pages that are unattached and start filling them to whatever fill factor we desire. So in our example, we'll create leaf pages that are 3/4 full. And when we get the leaf page full, we'll create a parent page to point to it. So here we've inserted 1, 2, and 3 in a leaf, and we've created a parent that points to that leaf. Then we took 4, 5, and 6, and we put them on the next leaf, and we put the key 4 and a parent and a pointer in the parent. Same thing with 7, 8, 9, 10, 11, 12 with parent index entry 10, 13, 14, 15. And when we create the next page now, 16, 17, 18, we're going to have to do something new. Particularly, we're going to have to build enough superstructure to hold this, which means we're going to split the original parent into 2 and create a new root in this case. All right, so we know how all that works. Notice that we don't have our occupancy invariant covered here, but that's okay because we're going to keep inserting things. So this is a temporary state. Notice also that as we keep inserting bigger and bigger values, 19, 20, 21, and so on, they'll all go to the right, which means that the pages on the left will never be touched again during our bulk insertion, which is really good because that means that they won't interfere with our buffer pool. They'll basically get paged out of the buffer pool, never to return, and only the stuff that's changing on the right fringe of the tree will be in the buffer pool. So we'll get nice locality in the buffer pool. Note also that the stuff on the left has its occupancy invariant maintained. The only place where the occupancy invariant is not true is on the far right fringe where we're doing further insertion. Okay, so that stuff on the left is essentially frozen for the bulk loading algorithm. We won't touch it again. And as we insert more things to the right, we'll just keep building the tree. And so to summarize, one option to do bulk loading is to do multiple inserts. This is going to be quite slow. Another side effect of doing multiple inserts is, as we've said in the B plus tree, we don't have sequential storage of the leaves. But with bulk loading, there should be fewer IOs during the build because we won't be doing as much random IO. So most of the times when we touch a page, that page will already be in the buffer pool. The leaves, if we do bulk loading, can actually be stored sequentially. So we can allocate a bunch of blank space and start filling it with leaves. And as we're building this tree, we can keep all those leaf nodes together. Now we don't have to because they have previous and next pointers, but we can. And what that means is that when we go left and right across the leaves, following previous and next pointers, we'll actually be moving sequentially on the disk and it'll go really fast. A final advantage of bulk loading is that we can control the fill factor on the pages. In the example, we did 3/4 full, but you could do half full, you could do completely full.